Hi friends! Are you currently a university student looking to pursue software engineering in the tech industry after graduation? Well, once upon a time, I was just like you. I've been in tech now for 10 years and worked at companies like Microsoft and Google, and now I'm so proud to say that I've been teaching at the University of Washington for 5 years teaching data structures and algorithms, specifically the class that I know as an engineering hiring manager mattered the most when I was conducting hundreds of interviews all over the industry. So we've made a bunch of videos to make sure that you can shine in the interview, and today's topic specifically about object-oriented design. So you can make sure that not only are you showcasing your coding credentials, but all of your critical thinking and design chops too. So what is object-oriented design? Or you might hear it referred to as object-oriented programming, abbreviated as OOP. Well, object-oriented design is really just a software design paradigm, or a fancy way of saying how to organize your large code base around this concept of objects. Object-oriented design has this idea that every piece of code is either a client or an object. An object has a certain set of abilities. We might call these behaviors or functions, and really they're just represented by the methods inside that class. These behaviors act upon the data or state, often just stored as fields. So an object is an item that has some amount of data that is stored about it, and then a series of methods that provide utility or take action on those fields. By separating our code into a series of objects, it's like we're sort of dividing and conquering all of the work that needs to be done. And it helps us break up our large code base. It also allows those objects to kind of be picked up and used by lots of different clients simply based on the utility that they provide. So I like to think of OOP as one big toolbox where we've taken all of your code and we've nicely organized it by its functionality. Everything is a specific role, and you know exactly where to find what you're looking for when it's time to leverage that functionality. So your entire code base looks like this nice collection of well laid out tools. The object itself, like I said, is maybe one of those specific tools, like let's say a wrench. And so the wrench's state might be how wide it's currently open to. It might store some information about like how small the opening can get, how wide it can get, what type of material it can adjust, things like that. And then its behavior would be the set of methods that provide the utility. And maybe that behavior is tightening a screw or loosening a screw. Maybe it's adjusting the width of the mouth between the two prongs. This way, the client doesn't need to re-implement or build their own way to adjust these screws. They simply need to reach into their toolbox and pull out their wrench. And when a new client comes along, they can reuse that wrench too. So this way, we sort of think about our code in terms of the utility it provides to other pieces of code, and as a client, the type of functionality we're looking for. So why object-oriented programming? Well, the biggest answer is modularity. In school, you're probably used to writing code that's maybe a few hundred lines long, but in industry, we're writing codes that's hundreds of thousands of lines long. When I used to work in office engineering for Microsoft, our code was 1 billion lines of code that all built together. And it was being worked on by over 4,000 engineers. Could you imagine if we were all trying to work in a single document? No, that would be crazy. Modularity lets us break up these huge code bases so that multiple people can work on it. Also, it's much easier to find bugs. Can you imagine trying to find a typo in a 1 billion line long document? Breaking our code apart into these logical units makes it easier to share the work with other engineers and also to maintain the code because it's much easier to find things. Object-oriented programming also really relies on the idea of abstraction. We are constantly asking ourselves, what role does this code play? What utility does this code provide? And then we need to think about, is this utility shared across other items? Does all of this utility have to be associated with itself? Once we start to explore the levels of abstraction, we can better organize our code and we can more adeptly leverage all of the code and reuse it so we're not just constantly rewriting very similar pieces of code. Remember, the more code we write, the more places there are for bugs and the more places we have to go looking for them. OOP is also, because of this modularity, really great at fine-grained encapsulation. Also, most object-oriented languages come with encapsulation features where you can specifically mark pieces of data, private, public, sometimes protected, so you can have a really specific level of control over what pieces of code can access what data. This not only works for just privacy and security reasons. You certainly wouldn't want every Facebook profile to be able to read everybody else's messages, things like that. But it also makes it so that other code doesn't need to know absolutely everything about every other piece of code. So we can hide what we need to hide to keep things simple and keep things safe. And then another big feature of OOP design is inheritance. This is the idea that we know code will share between different files. Inheritance sets up a hierarchy where code that is at the top of the hierarchy, or the parent code, will have really generic code, and then code that inherits from that object or class can take that generic usage and add on another layer. So as you work from sort of the top level ancestor all the way down to the most removed child class, you work from generic to more specific. And this is really helpful because this lets us take all of that logic and abstract it up so that it's shared across common ancestors. This really enables us to split apart our work on large teams, be able to find things in billions of lines of code, and also reuse code as much as possible so that we can keep that number of lines down. Now, if you're prepping for technical interviews, you've probably been told to review something called data structures. Well, what is a data structure? Simply, it's just a collection of data. Now, each data structure might have a different way to organize things, just like you might find you have a different way to organize your closet from someone else, and you might be optimizing for different things. Different data structures might optimize for order or quick access or ways to associate data or find pairings or relationships. And we, in other videos, are going to explore all of the wide array of different data structures and all the different things they optimize for. Here are some common data structures you might have heard of. An array, a linked list, a tree, a hash table. These are all very different ways to store related pieces of data, and each is really good at some things and not so great at other things. So picking the right one for our scenario is a core skill for being great at object-oriented design. Most people jump straight to the data structure, but the data structure is just how items are held together. A lot of times people forget to think about what functionality you want your structure to provide. And that is typically expressed in something we would call an ADT, or an abstract data type. An abstract data type is just a detailed model of the functionality of a given object, which is just a fancy way of saying, hey, we as developers have all agreed on a certain set of utility or functionality or just methods that anything that calls itself by this name has to implement. Here are some common ADTs you might have already been using: list, set, dictionary, stack, queue. For example, a set is a collection of unordered items that must be unique. Now, in no way did I talk about how those items were stored, just said what they are required to be able to provide to the user. Once I've decided my functionality, then I should look at my list of data structures and pick which one is going to be best fit for my scenario. Here's another way to think about the distinction between ADTs and data structures. Let's imagine you are trying to figure out how to get from point A to point B. So you know you need some mode of transportation, and you want this mode of transportation to be able to move and also to be able to be steered. That seems like at least the bare requirements of functionality to get you from point A to point B. That's just the list of requirements. That's just the list of functionality. It doesn't say anything about how you're going to accomplish that. But once I know what I need to accomplish, then I can look at the actual implementation and figure out what's best for my needs. So in terms of transportation, I could have a car that uses tires and a steering wheel. I could have an airplane that uses wings and like the control joystick. I could have a bike that has, sort of wheels with spokes and handlebars. And each of those might be optimized for my specific need. If I'm just going down the block, probably I'll pick the bicycle. I'm optimized for fast and easy. If I want to go to the next town over, maybe I'll pick a car. If I want to cross over an ocean, I'll pick an airplane. All of those things are still accomplishing from A to B and being able to be steered, but I can pick an implementation right-sized for my needs. So this is the order you always want to think about your object-oriented design. First, what is the utility you're working with? Because that's how we often organize our objects. And then, what data structure am I going to use to actually implement that utility so that I can optimize it for exactly the use case I'm designing for? In Java specifically, you can formalize an ADT in code in what we would refer to as an interface. An interface is a Java construct that just lets you list out functionality without any implementation details, and then any class or object that implements that interface will then be viewed and known to have that functionality by any client. So here's what an interface looks like syntactically. It looks a lot like a class, but you can see what it does is it has a name and then just a series of method headers. But at the end of the method header, there's just a semicolon, no curly brace, because I'm just telling you what this object can do, not how it does it. Then, when you are writing your objects and you want them to be categorized according to their functionality, you can have them implement the interface. So let's say we were writing an interface called shape. And shape defines all shapes as having some amount of area and some amount of perimeter. I can then go and write 4 separate objects like the circle, the rectangle, the square, the triangle, and each of those could implement the shape interface so I know that they will have some piece of information about their area and some piece of information about their perimeter, but I'll let each of them determine how to distinguish those values. As you can imagine, the formulas for figuring out the area of a circle, different than a triangle, but I still need to know that both of those can tell me their area. I just don't care how they accomplish it. Now that we know a little bit more about ADTs and data structures, let's look at how we actually instantiate or create these magical data structures that we're going to use in our interview solutions. So here are some examples of how you would actually create a new object that you can start to fill with your own data in Java. So here you can see if I want to make a list, I am going to use an object that I know implements the list interface. It happens to be called ArrayList. So I'm going to make my object type the ArrayList and my declared type list. That way, this variable knows that it will have the list functionality, but under the hood, I know that the ArrayList is what's doing the implementation. Let's dive a little bit deeper into this list ADT so we can get into more of a case study. So the list ADT in particular dictates that a list is a collection of ordered elements that all have their own index. So you can kind of picture it like this. It's a bunch of objects in a sort of like linear progression. The first item is at index 0 and it extends beyond that, but it's pretty flexible. You can add something to the front, you can add it to the back. If you want, you can insert it in the middle and everything to the right of it will kind of shift over to maintain that order. So a list becomes a really useful type of ADT, but there's a lot of ways in code that we can manage this type of functionality. Here is that same functionality, but more explicitly written out in terms of the methods that need to get implemented. So we need to be able to grab something from the middle of the list, given the specific index. We need to be able to insert, append, all of that stuff. And you can see here how those things would be articulated in the actual code that would define the list interface maybe your eventual data structure will implement. So let's talk about how you would actually implement the list ADT using the world's most popular data structure, the array. So if we're going to use the array, that means that where we're actually storing our pieces of information is in an array. But the list requires that we are able to insert something, it's able to grow and shrink in size, but we know that an array as a data structure is statically sized, meaning once you make your array of a certain size, it can't really grow or shrink beyond that. So as we're writing our code, we will need to add the functionality that accommodates the list ADT, even though we're working with the array underneath the hood. So what we're going to do is we will declare an array larger than we actually need. Like, let's say we start at a default capacity of 10 items. Initially, that array is totally empty. It's going to be full of zeros. When I add my first item using the append or the insert or the add, then what's going to happen is I will put that item at index 0, and I will have a second field called size that I will maintain, and I will increment that to 1. Now, I can tell the difference between how many items are actually stored in the array and the overall capacity of the array. Then, as I continue to add things, I can add them at indices, I can shift things over, but I will continue to maintain the list between index 0 and index size minus 1. And everything from size onward will be sort of beyond the capacity of the list, though still within the given array. Eventually, we may fill up the array. If we fill up the array, then what we will do is we'll make a brand new array that's probably about twice the size of the original one, copy everything over, and now we've got extra size. So with the array list implementation, you're always sort of maintaining this extra bit of storage padding and filling it up until you run out of space in that array. And because arrays can't grow or shrink, then we'll just make a brand new array that's twice the size. Now let's explore implementing the list ADT with what we would refer to as the linked list data structure, which is really just a series of node objects that store a reference to the next node within themselves. So the way that we would create the list in this context is instead of using an array, we will have two fields. Again, one that just maintains how many items are stored for size. But instead of the array, we're just going to store a reference to the first node in our linked list. Now, there are a lot of different types of linked lists. I'm going to be talking about singularly null terminated lists, but you could also add a back pointer if you wanted to easily access the back. Some linked lists have double pointers, both front and back per node. And so it's up to you depending on your situation. But the classic example is where we just maintain a singular direction of references and we only store one overall field, the reference to the front node. Now, anytime we append or add, we'll make a new node object, but we'll only ever make one when we need a new item. So we don't have to maintain that kind of padding or extra space that the array did. Plus, now I can move things around. It's much easier to delete things. I don't have to do any shifting to maintain order, but the array was really nice because it came with its own indices already attached. And the list ADT does require, even if you're using a linked list, that I should be able to give you an index and you should be able to give me that object, even if it's in the middle. And since linked lists don't have indices and we only have a reference to the front, in order to get to the middle of a linked list, I'm going to have to make a current or a temp pointer started at the front node and then loop and count until I get to the index that I want. So I kind of trade away the ease of the indices that come with an array, but gain the flexibility that comes with just changing references of nodes and also that nice right-sized memory usage because I don't have to maintain a mostly empty array. Let's take another level deeper in how we would actually implement these things. So let's say we want to insert an item. In this case, we want to insert an item at index 0. Well, remember, a list requires that we maintain order. So if we insert at 0, the value 10, we know that we ultimately want this list then to read 10, 3, 4, 5. So to make that happen in the array, because index 0, 1, and 2 are already full, I need to perform a shift where I make a sort of space and then insert the 10 in. So what I'm going to do is I am going to recognize that because I'm using insert, the size of my list is going to grow by 1. So I know eventually I will need up through index 3. And right now I'm not storing anything in index 3. So I'm going to make a copy of value 5. And now I have 2 copies of value 5, which is great because I can get rid of one. Let's say replace the old 5 with a copy of 4. So I still have 4, but now I have 2 copies, and whenever I have 2 copies, that means I can delete the old one. So now I can make a copy of 3. And I've kind of shifted the 3, 4, 5. Now, instead of being in indices 0, 1, and 2, they're in indices 1, 2, and 3. And my old copy of 3 is in index 0. I don't need that one anymore. Now I can just drop my 10 in there, and then I can increase the number of items stored in my array. So because arrays are all sort of contiguous memory stored right up against each other, if I want to insert or make a space for something, it does mean I might have to shift all the other values in order to make that space happen. Versus if we compare to the linked list, if I want to insert at index 0, well, I know index 0 should always just be what front is pointing at. So I'll just make a new node and point front to it and have the new node point to what front was previously pointing at. And then update my size. Let's talk about delete. So again, let's delete at index 0. Now we need to maintain the sequence, which means I need the new first item in the list to move eventually into index 0 so that it will still read from index 0 on the correct ordering of my list. Now in this case, I'm deleting data, so I don't need that 10 anymore. So I can do the same copy shift thing I did for insert, but I'm gonna go to the left instead of to the right. So I don't need 10, so I'll make a copy of the 3, move that over, and now I can change the old 3 by moving the 4 into the 1's place, and now I can change the old 4 by moving the 5 into the 2's place. Now here, you might be tempted to go in and try and clear out that 5 stored at index 3, but because I'm going to maintain a size variable, I can know that everything between 0 and size minus 1 is sort of in play or within the valid bounds of the list. And everything beyond that is trash or extra use or whatever. So I'm not even going to bother to get rid of the 5. That would be a waste of my time. It's sort of beyond the borders of what I care about. So I'll just change the size to 3. And now my list correctly reads 3, 4, 5 starting from index 0. And I don't care what's stored at index 3 anymore. It'll eventually just get overwritten if I add something new to the array. With the linked list implementation, if I want to remove a node, well, I just tell front to skip it. Really convenient. Very convenient in this case because what we were removing happened to be at index 0. But if instead I had wanted to remove the 5 or the thing at the very end of the linked list, remember there's no indices. So I would have had to make that temp pointer and then loop it all the way until the end. So I might have incurred a linear runtime in that direction if it had been a different thing I was deleting. Now let's talk about append. Again, append means to add to the very back of the list, and in this particular instance, I only gave myself a front pointer. So in order to figure out where I'm going to be able to append this to, I need a pointer that's pointing at the node with the 5 in it. And the only way to get there right now, because the only in I have is front, is I'll make a temp pointer pointed at the 10, and I will loop it until I get to my temp pointers.next field is null. Once I'm at that point, then I can make a new node and attach it to the very end. And then I can update the size. Now, the array can be a little different because at this point, let's say I want to append, but there's no space left in the array. I can't just grow the array. So this is a situation where we're going to have to create a brand new array. The convention is to make one of double the size. And then I will copy each of the items over in turn, maintaining the order. And now all I've done is sort of duplicate the previous list that I have, but just give myself more array capacity. So great, I can just pop that new item right there at the end. When you're creating this new array, people will often ask, well, why don't I just make an array of one size bigger. So instead of here, where I went from a size capacity of 4 to a capacity of 8, why didn't I just go from a capacity of 4 to a capacity of 5? Well, if you saw, making a new array and copying everything over is really runtime expensive. That's a linear runtime. We had to move everybody. Imagine you're at the movies and you stood up and you had to make everybody stand up to get out of the aisle. You don't want to do that all the time. So we're going to pick a size to grow so I don't have to do that quite so often. It's such an expensive action. But I don't want to make it so big that I never resize, because then that means I've told my computer to set aside a huge amount of space that I may never use, and who knows what I could use that memory for. So the convention tells us that traditionally we just double the size of the array, trying to find that balance between not having to do this that often and also not wasting too much space. Let's talk about these types of trade-offs in terms of big O notation. You've heard me mention constant or linear, but I'm always going to use the big O notation. That is what you will be expected to use in interviews. So the time to access the nth element, where n represents the number of elements stored in the list, well, in an array list, because the array is the underlying structure, I just need which index. And then I can just jump right in and access that element. And accessing a single element array is always constant time. It doesn't matter if that array has 10 items in it or 10,000. It takes the same amount of time to access the item at index 7, no matter how many items are before or after it. But the linked list, because I don't have those indices, I'm going to have to loop and count as I go until I find what I'm looking for. So in a worst case scenario, what if I was looking for the thing at the very end? Then I would have a linear runtime, because if I had to loop over a list of 10,000, that's going to be really different than a list of 10. So we would consider that O of n, or linear runtime. Time to insert at the nth element. Well, this, remember, because of the array and everything being stored right up against each other, if I'm going to insert, it's going to have to force everything to shift. So because everything's going to shift, everything's going to move, I'm going to have to loop over every item until I get to my spot. Again, that's going to have a linear runtime. It's going to be directly correlated in runtime to the amount of items stored in the array. 10 item array, going to be much faster than a 10 million item array. Now, inserting at the nth element for a linked list, we're going to have to incur, again, that loop to count up until we get to the nth location. So again, linear runtime. Now, I've talked a lot about runtime, but another thing you want to consider when you're doing your design is also memory usage. And this is a really important part of the OOP design, that we're always thinking about how we optimize for runtime and also how we optimize for memory storage. So if we're thinking about the overall amount of space used across the entire collection, well, with arrays, remember, it's like we kind of always have to maintain that extra bit of padding. So with the exception being right before you resize, you always are going to have some amount of wasted space, just so that you can add something new into the array. Different from the linked list, where you only ever make a new node when you have a new item. The other thing too is that traditionally, when we remove items from an array, we do not shrink the array down. That's because chances are, if there was something of that size already in the array, we'll use it again, and we want to avoid those expensive copying over things that we had to do. So that means that not only might we have unused space on the array as we grow bigger, but also if we delete a bunch of things, we might have grown really fast and then deleted a bunch of things and our array never shrank down. So we could have a lot of sort of just extra memory partitioned. Very different from the linked list, where whenever we need a new item, we make one new node, and whenever we don't want that item, we release that memory back to the computer. So the memory is much more right-sized per entries across the overall structure. However, when we look at each individual item, computers are really optimized for arrays, because computer memory is just a big array. And so when you ask your computer for an array of size 5, what it goes and does is actually find 5 spaces of memory right next to each other, so that you don't have to store any extra information of where to find those pieces scattered across your memory. So your memory per item is going to be the minimum amount required in the array list model, but in the linked list model, because you're only asking for a singular node at a time, your operating system might put your first node in one place in memory and your second node in a different place in memory, and it might be scattered all over, which is okay because each node maintains a next field to say where in memory to find who comes after it. But that means you have extra pieces of information you have to store per each individual item. And also, because that's non-contiguous memory, or it's memory sort of scattered all over by your operating system, it actually does just take more time to travel from one node in memory to another, as opposed to looping over contiguous memory right next to itself within the array. I kind of like to think of it as like bookshelves. Let's say the array list is a singular bookshelf. Well, bookshelves can't really grow or shrink, and you want to put books that are related right next to each other. So maybe you have empty space in your bookcase, but you can find all of the books by the same author really fast. If you have a linked list, you might be scattering those books all over. Maybe you have to walk across the library, who knows? But that will take longer to iterate through because of the way that the non-contiguous memory is organized. Let's put some of these trade-offs to good use when it comes to design. The ultimate goal of why we're learning to modularize, abstract, and encapsulate all of our code within the OOP organization. So let's say you've been asked to implement some type of software that will be used to store a list of songs in a playlist. Now we are going to tell you, we're going to ask you to use the list ADT, because that will give us the way to order things, get indices, add and remove, so on and so forth. But it's up to you to decide, do you want to use the array implementation of the list or the linked list implementation? So you might want to consider what you do most often with a playlist. Are you regularly adding a bunch of songs and then removing them or reordering them? Are you playing shuffle, so on and so forth? And there's no right or wrong answer to any of that. But in the context of an interview, you want to ask not only about what functionality is required, so you can pick the right ADT, but you also want to ask which functionality is going to be used the most, or which functionality has a really strict limit on how long it can take, or would it cause any crashes if it ran really slowly. So you kind of have to make sure that you're enabling all the functionality, optimizing for what's most important, and also respecting any boundaries around the total length of time that you can run. So let's say you pick array list for this context. That might make sense because, for example, everything has indices. So if you wanted to program shuffle, instead of moving things around, you could just generate a random list of numbers and jump into those places in the array without having to move things. Really fast and easy. Also, if you're just playing your playlist from start to finish, because of the difference between contiguous and non-contiguous memory, it'll be a lot faster for the computer to just start at index 0 and loop through all your songs in that order. But because of the shifting and all of those types of things, it might be a little bit harder to reorder your playlists or insert something. Maybe you're someone that really cares about the specific rise and fall of your playlist. Maybe for you, linked list is the right choice, because that's going to be a lot easier to move things around, change the order, insert. It's also going to be the right size. Maybe you have some playlists that are really small and some playlists that are really big, and a linked list tends to be a better choice when you have a wide variance of the overall capacity of your list. Let's look at design situation number 2. This time you're asked to write a piece of code that is going to store a customer's history of bank transactions. So in this situation, you know that order is really important. Again, we're going to pick the list ADT to maintain that order, and so that maybe, we can use the indices to look things up at later times. But let's think about the scenario in a little more detail. We know that maybe if you're someone that needs to be able to jump into the middle or do these types of audits, it would be nice to have those indices to be able to jump in the middle, especially in what's probably going to be a very long list. Also, chances are, as you get really big, it's always going to be growing. So the array that always grows might be a better fit. You don't have to worry about it removing transactions. Hopefully you're not editing history. So an array might be an okay memory usage in that context. A linked list, depending on how you implement it, You could just get that constant time additions if you're always just adding to the front, and maybe you recognize that you're only ever really looking at the items from pretty recent transactions. So if you add them to the front, meaning sort of in that reverse order, then maybe you're only ever interacting with the first few nodes or the first 4 or 5 or something like that as the list grows longer and longer. And you don't very often look at super old transactions. You don't have to really loop all the way to the end that often. So you can see that there really isn't any right answer. It depends on how you make those design choices. And in an interview, make sure that you ask those questions and you clarify your assertions as to why you're optimizing for what you are. Okay, let's finish it up with our final example here. Let's say you've been asked to implement a way for students at a tutoring center to sign up to wait to speak to a TA. Now, this is an interesting one where you have TAs maybe pulling students off of the front of the list and you have students maybe adding themselves to the back, but maybe you're not so often looking in the middle, things like that. Now, also tutoring centers tend to have a pretty limited capacity, and so you could probably guess at the overall capacity of that array. It's not going to get too big overall, and so maybe it's really nice and memory efficient to just use the array list. But a linked list, you could very easily add and remove if you added a front pointer and a back pointer. If you have the 2-pointer system, then you have a constant remove from the front and a constant add to the back as long as you maintain those pointers. So totally up to you which one you want to optimize for and how you want to implement it. This is just a basic intro into how you want to think about the initial design for the solutions to your interview problem. Make sure that you ask lots of questions, make sure you pick the right ADT that enables your functionality, and ask a ton of questions of your interviewer, and always state your assertions about why you're optimizing for what particular implementation. And picking this right combination is what's going to set you on the path to a fully functioning and optimized solution. Thanks so much for studying with us today, and best of luck on your interviews.